let's check at it. In this video, we're going to be talking about controllability. This is this idea we're starting to move away from just basic analysis of dynamic systems and starting to think about if these systems have properties that we don't like and we want to change them, can we change those systems' properties, and can we make the system do what we want? Can we basically drive the outputs and states to whatever values we want? And that's where this discussion of controllability comes in. So we're going to be looking at this system. We're going to look at x dot, and this is all continuous time in this video, and we're all sticking with LTI systems. So ax plus bu, and we're not going to worry about y equals cx plus du because we actually are more interested in the ability to move the entire state vector, not just some subset or linear combination of those states, which is what y would give us. So can we just control all of the states? So we're going to be assuming A is some n by n matrix, and B is some n by p matrix, so we have p inputs and n states. And the real question is, can we move our state vector, x, to any desired value? And this is an n by 1 thing, and so we really mean can we move all of the n individual elements to any desired value. So it's really easy if x is just a 1 by 1 vector, so we should have a single state. It's really easy to move it to some desired value. If I think about, I have time and I have my state, and let's say I want to get to this value here. It's pretty easy to figure out which input drives you in this direction and which input drives you in this direction, and as long as you drive your inputs in the right direction, it's pretty easy to imagine that after some amount of time, you can get your single state to the place you want. But what if you have two states? Then things become more complicated. Let's say here's where x1 begins, and let's say this is where state 2 begins, and I want to get state 1 to here. And I want to get state 2, so I want to get x state 1 to this value, and I want to get state 2 to this value. It isn't totally obvious that I can drive my system such that somehow this evolves up here, and this is also evolving like this. It could be that when I drive this state to go like this state does something else that I don't like. And so then the question becomes, can we get every element in x? If x is an n by 1 thing, can we get every element to some desired value with the u vector that we have? Does u have to be n-dimensional? Basically, do we have to have as many inputs as we have states? We're used to thinking about these kind of problems, kind of, three equations with three unknown kind of problems. But is it possible that I could somehow drive two states, both to their desired value, with only a single input? It turns out sometimes that is possible, and that's what we're going to be talking about in this lecture. And so some of these kind of notions are kind of counterintuitive, that a single input could drive multiple states to their desired value, but it is in fact possible. So in this discussion of controllability, we're going to be talking about the pair AB. So we don't talk about, what we can say is our system controllable, but we're not looking at our C or D matrix at all, and we're not only looking at our A matrix. So it's this relationship between A, which sort of encapsulates our inherent system natural properties, and B, which is where inputs influence those states. And so we talk about the pair AB, and we say that this matrix is controllable. This is the definition of controllable. If any initial state, so I have some initial state, x at times 0, which I'll just call x naught. I have any initial state, and I have some desired state that I want to get to. And remember, this is an n by 1 thing, so it's n desired states, really. So I have some initial condition, and I have some final state. If this system is controllable, then there does exist an input that transfers our system from the initial state to the final state in some finite time. And we're not saying that finite time is fast necessarily, but time does exist. It doesn't take to infinity. So if my system is controllable, then yes, I can move from this state to this state. And if it's not controllable, then it's not guaranteed that I can do that operation. So saying that a system is controllable doesn't say anything about the type of trajectory that you take to go from the initial state to the desired state. It doesn't say anything about how much time it takes, except for that it's not infinity. And it doesn't say anything about how big that your inputs you have to be. And it turns out, which is kind of intuitive, that if you want to make your states go from the final to the desired very fast, it's probably going to take very big inputs to do that. That's kind of an intuitive notion. So there are three equivalencies that we're going to use for controllability, and they're sort of all synonym ways to describe if this pair AB is controllable. So the first one that we're going to look at is the most common, and we say that this controllability matrix, I'm going to use this kind of script C, which we line up the B matrix followed by the AB matrix, and we go all the way up to the power of A to the n minus 1 times B. Look at this matrix. So this thing here is an n by p matrix, and this A is n by n, and B is n by p. So this is also n by p. So each of these elements are n by p, n by p, n by p, n by p. And there's up to n minus 1 of them. So this C matrix is n by n times p. So it has n rows and has n times p columns. The fewest number of inputs we can have is 1. So at the smallest, this is a square matrix. This C matrix is a square matrix. It's n by n. But in general, it's going to have n rows and probably more columns. So this controllability matrix, if it has full rank, so really, I can say full rank, but when you realize that there's always less than or equal to rows that are all columns, then this is the same thing as saying full row rank. Meaning I have to have, all of my rows have to be linearly independent. So, and this is our rank n, because that's the number of rows. So if this controllability matrix is rank n, then the system is controllable. And if it's ranked less than n, it's not controllable. So this is the first way we'll be able to talk about controllability, and this is by far the most useful in practice. It's pretty easy to see that, I mean, if you're given A and B, there's no hard math here to do. You just stack these things up, look at the rank, and you can see immediately if this thing is controllable. There are two other ways that we can describe controllability, and they're more useful sometimes for proofs. So if you're going to do research in this area, you want to be aware of these other two ways to describe controllability. So a second way is there's this n by n matrix, WC, evaluated at t, and this is defined from 0 to t of e to the a tau, b transpose, e to the a transpose tau, d tau. So this is just a matrix that's defined like this. And this is also the exact same as saying this is e to the a d minus tau, b transpose, e to the a transpose, d minus tau, d tau. These are the same matrix. So if this matrix here is non-singular, it's an n by n matrix, so non-singular means it can be inverted for any t, any t greater than 0. It doesn't have to happen to every t. If you can just even find one t for which this n by n matrix is invertible, then this system is controllable. And I think I'll stick with this discussion for just a minute, and I'll come back to the third way we can describe controllability. So this way we just described, it turns out if that thing is invertible, so let's say that WC inverse exists, so it's invertible at some t, then we can explicitly find a solution for u that does exactly the task we want, which is drive this from our initial state to our final state. So, and the way you do that, the input looks like that u of t should be equal to minus b transpose, e to the a transpose, t 1 minus t, so let's say that t1 is the value that this inverse exists for that you found. So if I just do this substitution and solve for this u, and now this thing exists at t1, and then I multiply that by e to the a t1, and this should probably seem completely strange and arbitrary here, and this is the desired state that I want to get to at that time 1. So basically this is probably done originally for inspection. So as long as this thing exists, then you can try to put in this u, and if you go back to our original, let's recall the general solution for our state evolving at time 1, it's going to look like e to the a at t1 times x naught, and sorry, I wrote x naught differently here, it's the same x naught, plus the integral from 0 to t1, e to the a, t1 minus tau, b, u at tau, d tau. So this is the general solution that we've seen over and over for this, the equation for x evolving at t. And it's true at all t, so I can explicitly look at this one specific t, t1. So I have t1 here, 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 here. And basically, if you take this u of t, which is hinging on this WC matrix exists, and you plug this u of t into this function, what you will get is you'll get a bunch of stuff to cancel out. And I'm not going to waste time doing that. And what you'll get is you'll get something that simplifies to look like this. You'll get that x at time 1 equals e to the a at t1 times x naught minus e to the a at t1 times x naught plus x1, which is our desired value at time 1, and of course these things cancel out, and that equals x1. So basically someone said, you know, what do I have to do? What kind of input do I have to have so that this thing will completely cancel out, and my x at t1 is exactly the value that I want to have, the desired value. And they said, well, if I found a u that looks something like this, then all this stuff will cancel out properly. And they said, okay, well, what would this thing need to look like to make all that cancel? And that's where this WC is coming in. So sometimes the second definition of controllability can be useful for proofs and things, and the third can also be useful for proofs. And that third definition of controllability looks like this. The n by n plus p, so n rows and n plus p columns, matrix A minus lambda I B has full row rank at every eigenvalue. Of A. So it turns out if this thing is solved, then you also have controllability. And so you have these 3 equivalent ways to describe controllability. Some are going to be more useful to others than others in different contexts, basically. So and we've said if a system is controllable, then there does exist a u that drives your system from the initial state, and it's not the initial state, it's any initial state, to any desired final state. You don't know how long it's going to take, and you don't know how big u is going to be. So the one thing that's kind of important to note is that because this final time, we saw in this last example with the invertible WC matrix, that final time t1 was a completely arbitrary number. And if that number is arbitrary, we can make anything. We can't make it 0, but if we want to make it 10 seconds, we can make it 10. If we want to make it 1 second, we make it 1. What will happen is the u that you get will get really large, but that final time is completely arbitrary. So this idea of controllability, while it originally didn't say anything about how fast you can get to the final position, it turns out after you start thinking about it deeper, you say, if I can do it at all, then I can just basically speed up the process. So once you figure out that you can do it as fast as you want. So the one thing I want to sort of make note of at this point is at this point we still aren't really talking about real control systems yet. We're just talking about the ability of a system to be controlled. So we're not actually proposing a controller. You know, I've yet to say to you how you would generate this u, but just that the u exists. So we're still kind of living in the land of analyzing linear systems, sort of types of properties they have. And we spend a lot of time in this class, basically the first half of the semester, just analyzing the properties of linear systems. And once we understand those properties, then it makes it useful to us to actually start designing controllers that will actually choose this u for us to make us get to the state that we want. So the most useful condition to us was this controllability condition that said if I stack up b and ab all the way to a to the n minus 1b, if this thing has full row rank, then it's controllable. It turns out there's actually sometimes a smaller matrix that we can look at that we can also analyze for full rank. If that matrix is controllable, that's just as good. What it basically means is because there's so many more columns in it sometimes than there are rows, it doesn't make sense to keep multiplying and add more and more columns. You'll sort of know if it's going to be full row rank just after you work first on so many left entries of this. And the logic of this goes like this. We can safely assume that the matrix B has full column rank. So why can we do that? If we had a matrix B, so let me write that down. B has full column rank. And how many columns do we have? We have p columns. So we have p inputs, which means we have p columns. And if we were to have more, if we didn't have full rank, I mean, think what that would mean. Like, let's say our B matrix looked like this. It looked like 1, 0, 0, and 1, 0, 0. I have 2 inputs. So this does not have full column rank. Why would you ever do this? Because basically, u1 can affect x1 dot, and u2 affects x1 dot in the exact same way, and neither of them affect x2 dot or x3 dot. So these two u's, what's the point of having 2 separate inputs? If you ever had a situation like this, you just go, I don't need 2 motors for this. I would just have 1 motor. And so you never make a system that didn't have full column rank, because if ever one of your columns was some linear combination of other columns, that really means you have 1 input too many, and you just wouldn't use that input. So it's safe to assume that this matrix B has full column rank p. And since this controllability matrix has n rows that has n times p columns, remember this was n by np, so it has n rows and n by p columns, it will have linearly dependent columns if p is greater than 1. So if we have, because let's say it's got 4 rows and there are 2 inputs, so that means there are 4 rows and there are 8 columns. But if you have a 4 by 8 matrix, the biggest rank it could ever have is 4. If every row is linearly independent, then it will be rank 4. But that means there's also only 4 linearly independent columns. You can't have 8 linearly independent columns. So it'll have, if as long as p is greater than 1, all of these cases where p is greater than 1, it can't have a rank higher than n. So really we only have to see if the first n minus p plus 1 rows have rank n. I think I meant to say columns. So what we say, so we can basically make a simplified version of this, understanding that there's way more columns than there are rows, and a simplified version of this is say, let's look at this controllability matrix, which is equal to b, ab, and instead of going all the way to a to the n minus 1 power, let's just only go to the a to the n minus t power. So if we look at this matrix, if this has rank n, then it's controllable. So basically we can sort of save time. If we only have 1 input, then we do actually have to do this, and this will be an n by n matrix because b is 1. But if we have more than 1 input, we don't need to carry out all of this math. We don't need to keep basically multiplying a by itself. We can just stop at n minus p and analyze that matrix. We're essentially sort of just picking off a left part of this matrix. So it just makes your life a little simpler in working these things out. The final thing I want to talk about is that controllability is invariant to equivalence transformations. This is what we keep finding in this class over and over, is that if I just do a linear transformation and say I'm going to convert my A to some A tilde equals Q A Q inverse, and I'm going to convert B and C properly, as we've learned in the past. If you do that, the properties fundamentally don't change. Your system eigenvalues don't change. The Jordan form of the matrix is the same. The stability doesn't change, and it shouldn't be surprising that the controllability doesn't change. I mean, what we're really learning over and over and over again is that all equivalence transformation does is repackages the same information in slightly different ways. We can look at our system a little differently, but there's no new information and there's no information lost. And this is really easy to show. I mean, if you have this controllability matrix, script C equals B, AB through A to the n minus 1B, and you do this substitution here, you get something that looks like, and you do the other substitutions of the equivalence transformation, you get something that looks like Q inverse B tilde, and then the next term looks like Q inverse A tilde Q, and then Q inverse B tilde. So this is using this relationship here that B is equal to Q inverse B tilde, or that's the same thing as saying B tilde is equal to BQ. So I'm doing this plugging in here, and I do that all the way. Eventually you start having these things cancel out, and you have something that looks like A tilde to n minus 1 Q inverse. You have this kind of pattern repeating, and then you realize that all of these, anytime you see this, that goes to the identity matrix. And so what you're left with is this controllability. I can factor this Q inverse out from the left of every single term, and so if I do that, I'll get Q inverse times B tilde, A tilde B tilde, all the way to n minus 1 B tilde. And then I can call this matrix here the controllability matrix sort of equivalent, and then I acknowledge that I can say C equals Q inverse C tilde, and that's the same thing as saying controllability tilde is equal to controllability Q. And then what I'm fundamentally doing here is I'm utilizing the fact that if I multiply any matrix by an invertible matrix, so Q is an invertible matrix, then its rank doesn't change because it's invertible. So I don't lose or gain information. So if I take, oh sorry, this should just be regular C. If I take my controllability matrix and I multiply it by Q, I get this new equivalent controllability matrix, but they have the exact same rank as each other. So if I analyze the rank of this matrix, I get the same answer as the rank of this matrix, which is ultimately what's leading me to the statement my system is or isn't controllable is the rank of this matrix. So it's really easy to show that this equivalence transformation doesn't affect it. Another thing that's really easy to show, and I'm not even going to bother doing it, I'm just going to end saying, it's really easy to show that reordering the columns doesn't do anything to controllability, the columns of your system, like your B matrix. So I mean, effectively reordering the columns of your B matrix would just be something like calling input 1, input 2, and calling input 2, input 1. Just renaming things doesn't fundamentally change your ability to control your states. So that's the end of this discussion on controllability of continuous time systems. I'll make another video about the controllability of discrete time, and it's just a small modification of this technique, but it's the underlying truths are the same in that concept.